Welcome to the deep dive. Our mission today really is to cut through some of the complexity and get right into some truly cutting-edge physics.
hmm
We're diving into the latest results from the ATL's collaboration at CERN. You might have seen the report from SciTech Daily.
Right, really exciting stuff coming out of Marseille.
Exactly. Think of this as your shortcut, to understanding what's happening right at the frontier
Yeah.
and how it might just reshape our view of the universe. We're talking Higgs boson, obviously, but specifically, these incredibly rare events.
And the hints of, well, maybe new physics, that's the tantalizing part.
So let's just quickly set the stage. The Higgs boson, we hear about it all the time, gives mass to other particles.
The cornerstone, in many ways, of the Standard Model's explanation for mass.
But studying it, especially when it decays in these really uncommon ways, I mean, how do they even do that? ATL's just presented two new studies, right, at the EPS-HEP conference in Marseille.
That's right, focusing on decays that happen very infrequently.
And why focus on the rare stuff? Isn't it important to just confirm the common decays?
Well, yes, confirming is crucial, but these exceptionally uncommon decays, that's where things get really interesting. It's not just about ticking boxes on the Standard Model, it's about pushing beyond it.
Ah, okay. Looking for cracks in the theory.
Exactly. These rare events are like little whispers, hints that maybe there's more going on than the Standard Model describes. They offer sort of unique insights that the more common interactions just don't.
Okay, let's unpack the first one then. This Higgs decaying into a pair of muons. H to mu, is that the short end?
Yeah, that's one.
And you said rare. How rare are we talking? Like really rare?
Oh, incredibly rare. We're talking roughly one time out of every 5,000 Higgs decays.
Wow. 1 in 5,000.
Yeah.
That's like finding a needle in an astronomical haystack.
That's a pretty good analogy, actually. You're sifting through mountains of data for this tiny signal.
So why bother? If it's that rare, what makes the H to mu decay so important?
Well, what's fascinating, really, is that this specific decay gives us the most direct look at how the Higgs interacts with what we call second-generation fermions.
Second generation. Okay, so particles come in generations.
That's right. 3 generations, each heavier than the last. Think electrons and up-down quarks in the first, muons and charm-strange quarks in the second, and then the tau lepton and top-bottom quarks in the third.
Got it. And we already knew the Higgs interacted with the third generation.
Yes, exactly. The heavier ones, like the top quark, bottom quark, tau lepton, those interactions were confirmed. But muons, they're in that lighter second generation.
Ah, I see. So seeing the Higgs interact with muons confirms it works for the lighter guys too.
Precisely. It helps us test if our understanding of mass generation holds true across different families, different weights. It's fundamental to figuring out why particles have the specific masses they do. It's a big piece of the puzzle.
Does it help explain why, say, electrons are so light compared to the top quark? Is that part of it?
It's definitely connected. Understanding these couplings across generations is key to that bigger picture. But the challenge is huge.
The detection, you mean?
Yeah, the detection. You're looking for this tiny, tiny bump in the data right at 125 GeV, that's the Higgs mass, and it's sitting on top of this huge background of other muon pairs being created all the time.
Right, just random noise, basically.
Yeah.
Or other processes creating muon.
Other much more common processes. So picking out that Higgs signal, it's tough. You need incredible precision. Sometimes you see these event displays, these pictures from the detector with distinctive retracts showing the muons. That helps visualize it.
So what's the news from ATLS? Have they found it definitively?
Well, they found strong evidence combining the data from Run 2 and the first 3 years of Run 3.
So a lot more data crunched together.
A lot more. And they're seeing evidence for HEMON with what they call an observed significance of 3.4 standard deviations.
Okay, 3.4 sigma. What does that mean in, like, normal terms?
It means the chance that what they're seeing is just a random fluke, a statistical fluctuation, is less than 1 in 3,000.
Wow. Okay, so not quite the discovery threshold, which is 5 sigma, right?
Not quite 5 sigma, no, but 3.4 is very solid evidence. It's a big step up from earlier hints. It really strengthens the case that, yes, the Higgs does couple to second-generation muons as expected.
Okay, that's one down. Now, the second decay, you mentioned it might be even more profound. Higgs to a Z boson and a photon.
AJO.
Yes, H to Z gamma. And the Z then decays, usually into electrons or muons.
What makes this one potentially point towards new physics?
Okay, so this decay is different. It doesn't happen directly. It happens through what physicists call an intermediate loop of virtual particles.
Virtual particles, like particles that aren't really there.
Sort of. They pop into and out of existence very briefly, allowed by quantum mechanics.
Mm.
They're too fleeting to see directly, but they mediate the interaction. They influence how it happens.
Now, here's the really compelling part. The standard model predicts which virtual particles should be in that loop, mostly top quarks and W bosons. But if there are other undiscovered heavy particles out there...
Particles not in the standard model.
Exactly. Maybe particles related to dark matter, or maybe heavier versions of known particles, or something completely unexpected. If those particles exist, they could also participate in that loop.
And that would change things.
It could subtly change the rate, the probability of this Higgs Zγ decay happening. So if we measure this decay rate very precisely and it doesn't match the standard model prediction.
Boom. Evidence for new physics.
That's the idea. It becomes a sensitive, indirect probe for things we can't yet produce directly. It's like a little window into the unknown.
That sounds incredibly promising, but I bet it's hard to measure too.
Oh, very demanding. First, the Z boson only decays into the electrons or muons we need for this analysis about 6% of the time.
So already rare.
Already rare. And then photons. Well, in a busy detector like ATLS, a photon can look quite similar to a spray of other particles. Telling them apart requires really sophisticated techniques.
Like trying to pick out one specific firefly in a swarm of gnats, maybe?
Something like that, yeah. You need excellent detectors and very clever analysis. We see these amazing event displays sometimes, showing the electron-positron pair from the Z decay and the photon signature, really highlighting the complexity.
So what did ATLS find for this HE decay? Any hints of deviation?
Well, again, combining Run 2 and Run 3 data, they reported an excess of events corresponding to 2.5 standard deviations.
Okay, 2.5 sigma, so less significant than the muon result.
Less significant in terms of certainty, yes. It's more of a hint than strong evidence at this stage. But what's really important here is the sensitivity they achieved, meaning their measurement sets the tightest constraints yet on how often this decay could be happening. They've reached the most stringent expected sensitivity to date, as they put it. So even if they haven't seen a clear deviation yet, they are now measuring this process with unprecedented precision. They're getting closer and closer to the point where if there is new physics involved, they should be able to see its effect.
Right, pushing the boundaries of how precisely they can measure it.
Exactly. It narrows the possibilities.
It's just amazing the level of detail they're achieving. For both of these decays, how do they actually manage it? What's the secret sauce?
Well, there's no single secret sauce. It's more like a combination of incredible advancements.
Okay.
First, as we mentioned, combining the huge data sets from Run 2 and the first 3 years of Run 3. That sheer volume of data is critical.
More data, more chances to see rare things.
Precisely. Then, they developed better ways to simulate the background noise. If you can model the background more accurately, you can subtract it more effectively and see the tiny signal underneath.
Makes sense. Better understanding the haystack helps find the needle.
You got it. They also got smarter about sorting the data, looking at how the Higgs was produced, which can help isolate certain types of events, and refining the selection criteria, just getting better and better at picking out the candidate events from the billions of collisions.
So it's data, detectors, and clever analysis techniques all working together.
Absolutely. The official line sums it up well. Success comes from the large, excellent data set provided by the LHC, the outstanding efficiency and performance of the ATLAS experiment, and the use of novel analysis techniques. It's a huge collaborative effort.
These results really feel like they're pushing right up against the edge of what we know. It's just a glimpse, isn't it, into how the universe works at this incredibly fundamental level. And when you think about the sheer human effort involved, thousands of people, decades of work, it's pretty inspiring.
It really is. And, knowledge is great, but it's most valuable when we understand it and can see what it implies. These findings, they deepen our grasp on mass, on particle interactions, the basic rules of reality. And it just highlights, again, that there's always more to learn. Every result, even for these super rare processes, adds another piece to that giant cosmic jigsaw puzzle.
So thinking ahead, the LHC is still running. More data is coming. What else might the Higgs be hiding?
That's the billion-dollar question, isn't it?
Yeah. Could these rare decays, maybe the Z-gamma one especially, be the first crack that opens up a whole new understanding? Could they rewrite the rule book?
It's possible. That's the hope, the drive behind these precision measurements. You push the boundaries, you look in the corners, you measure things with exquisite accuracy. And you wait to see if the universe surprises you, if it deviates even slightly from the script we've written so far.
It's just mind-boggling to think that these tiny, fleeting events happening deep inside a detector could hold the key to understanding the whole cosmos.
From the infinitesimally small to the infinitely large. That's particle physics for you. Always full of surprises.